Let's define some terms here first of all. The acceleration is any change in velocity per unit time. Now, in regular life, accelerations are always making things faster and faster. That's what we mean by acceleration. However, in physics, that's not the case. Any change in velocity, any kind of change in speed and direction is going to be called an acceleration. Line number 2. Since velocity has two parts, you can accelerate if either one of those parts changes. So, if you change speed or if you change direction, then you experience acceleration. That speed can be changed either way, either faster or slower. The direction can be changed in any way whatsoever. Any change in speed and direction is going to be considered an acceleration. So line number 3. Is something accelerating if it's slowing down? Yes. It's an acceleration that causes any kind of change in speed and direction. Amusement park rides are generally aimed at giving you unique accelerations. That's what gives you the butterflies in the stomach kind of a feeling. It's all your guts sloshing around on the inside as you change speed or change direction. The ride Ragin' Cajun is not known as a really fast ride, but it is one of the more popular rides because it gives you such unique changes in direction. You're spinning as well as going on turns, as well as going up and down. A ride that suddenly gives you a increase in speed would be like vertical velocity. In fact, they have a sign right out their front gate where they talk about how it goes from 0 to 60 in like 2.5 seconds or something like that. Line number 5. The equation for acceleration is A equals delta V over t. A is the acceleration, delta V is the change in velocity, and then the t is the time. How long it takes to change the velocity by a certain amount. Now, in this case, with the delta V, we're only talking about a change in speed. We're not talking about a change in direction at all. It's just that the mathematics of discussing direction is a little bit more complicated than I want to have for this chapter. So all of our accelerations here are going to be due to a change in speed. Now, another way of writing the equation for acceleration is A equals V sub f minus V sub I divided by t. What we've done here is that we've taken the change in velocity and we've rewritten it as the final velocity minus the original velocity. So let's use these equations in a couple story problems. A car is traveling at 5 meters per second to the right. The driver presses on the gas pedal, and after 10 seconds, the car is going 35 meters per second. What is the acceleration? Okay, so the first step is to draw pictures. Here I have the car, and I have the origin right where it is initially in the story problem. And I'm going to do it in the customary fashion with positive to the right and negative to the left. I have a little bit of information written down already. I have the time of 10 seconds between this location and that location. Now I don't have the initial velocity or final velocity yet. So looking at the story problem, we have the 5 meters per second is the initial velocity, so I'm going to put that there. And the 35, that is the final velocity, so I'm going to put that over there. Now that we've written down what we know, 10, 5, and 35, now we have to write down what we're trying to find. And we're trying to find the variable a. So now we have to ask ourselves what equation will relate the known information with the unknown. Okay, again, we only have really one or two equations to choose from. And let's use this version. A equals V sub f minus V sub I over t. Substitute our numbers in. The 5 is going to go for the v sub f. Whoop, that's not right. The 5 is going to go in for the v sub I. The 35, that's the final velocity there. The 10 seconds is going to go in for the t there. The a is going to stay a letter because that's what we're trying to solve for. So putting all those numbers in, we get this. Now notice that I've written the units next to every number. I'm going to try to do that all the time throughout the whole year in physics. The units are just as important as the numbers in many cases. Okay, so do the subtraction on top. We get 30 divided by 10, and we get 3. But 3 what? So the number part of our answer is 3, but what's the unit for acceleration? Well, looking at the top, we have 35 meters per second minus 5 meters per second. On the top, then, we're going to have 30 meters per second divided by the 10 seconds. So we have meters per second divided by seconds. And let's just write it like that. Let's not try to combine things at the moment. This is a legitimate unit for acceleration. 3 meters per second per second. Whenever you see the fraction bar, you say the word per. So once again, the acceleration is 3 meters per second per second. And what does that mean? It means that the speed changes by 3 meters per second for every second that passes by. So going back to our answer here, this means that for every second that the car drives down the road, it's going to increase its speed by 3 meters per second. So if it ends up going 35 after 10 seconds, after another second, it's going to be going 38. After another second, be going 41. And then 44, and 47, and 50. Keep on going up by 3 meters per second every second that passes by. Now, this idea of meters per second is a little bit awkward, and we can reduce that down to a smaller unit. So here we have meters per second over seconds. We have a fraction being divided by one item. So let's rewrite this one item on the bottom as a fraction. So now we have a fraction divided by a fraction. And you can remember from your elementary days that dividing by a fraction is the same thing as multiplying by the reciprocal. So meters per second times 1 over seconds. To do that, we're going to multiply the tops, multiply the bottoms. On the top, meters times 1 is meters. On the bottom, seconds times seconds is going to be seconds squared. Remember, units can be multiplied together just like letters A, B, C. If we had the variables x times x, that'd be x squared. So seconds times seconds is seconds squared. This form of acceleration unit, meters per second squared, is the most common unit for acceleration, and we'll be using that a lot during the coming days. Other units of acceleration may be kilometers per hour per second. What this would mean is for every second that passes by, the speed changes by so many kilometers per hour. We could have miles per hour per second, miles per hour per minute, all different kinds of combinations. But we'd prefer to have this kind of a unit, where we have the distance over a time squared. And that's the most easy to deal with, the most easy to say. So let's try to do it that way. Okay, now, here's a situation that we're going to analyze in a couple different perspectives. A skateboarder takes physics and decides to apply his new knowledge to the sport. He attaches a 43cc motor to a skateboard. A 43cc motor is like that for a small scooter that could go, maybe 35 miles an hour. So the student pushes off and coasts at 2 meters per second. That's about 1 mile an hour. I take it back. That's about 4 miles an hour. Then he kicks in the engine. Within 4 seconds, he's going 9 meters per second, about 20 miles an hour. Find the acceleration of the skateboarder. Now notice in this problem that it doesn't say which way the skateboarder is going. Is the skateboarder going to the left or is he going to the right? Does it really matter? Does it matter? Let's figure it out both ways and see if we get the same answer. We can imagine the skateboarder going down the road, and one person is on one side of the road, another observer is on the other side of the road. So one observer sees the person going to the left, the other observer sees the person going to the right, but it's the exact same skateboarder going down the exact same road at the exact same time. Just different observers see them going in different perspectives. Okay, so according to the first observer, observer A, the initial velocity is going to the left, which is a negative 2 meters per second. However, on the other side of the street, observer B would see from his perspective going to the right a positive 2 meters per second. The final velocity, according to observer A, is to the left, negative 9 meters per second. Observer B on the other side of the road would see the skateboarder going to the right, or a positive 9 meters per second at the end. Will both of these observers see the same acceleration? Maybe. Well, let's see. Okay, we're going to start off with this equation for acceleration. V sub f is negative 9. V sub I is negative 2. So we have a double negative here. We end up with the acceleration of negative 1.75 meters per second squared. Okay, observer 2. Put in positive 9 for the final velocity, a positive 2 for the initial velocity, and the negative is in between. The same time, we end up with a positive 1.75 meters per second squared in this case. So the acceleration is different according to what perspective you have. Therefore, the positive or negative acceleration cannot mean speeding up or slowing down. Because here we have the exact same skateboarder speeding up, but one observer says it's a negative acceleration. The other observer says it's a positive acceleration. So let me say this one more time. The positive and negative does not mean speeding up or slowing down. It means something different. Let's try to figure out what these positives and negatives really do mean. So, line number 11.